This is a lesson on substitution in the quadratic form. I'm going to remind you about the quadratic form. For all intents and purposes, what I'm going to be looking for in this lesson, or what you will train your eyes to look more commonly for, is the general form, where I have an a, a b, and a c in the function. Okay, and so what I'm introducing to you, as your precalculus teacher, I'm laying the foundation early in your math career for u-substitution. U-substitution is what we're going to do is use a simple variable to represent a more complex expression to make another math strategy easier to execute. Okay, so that's pretty abstract. For me, it makes sense, but for you kind of looking at it, you're like, what the heck was that English? So what we're going to do is we're going to initially make a substitution, but then eventually need to undo that substitution. That's the general idea of a u-substitution, is we're going to initially make a substitution, we're going to do another math strategy, and then we're going to undo our substitution. And what this looks like, it's similar to decomposition of functions. You've done decomposition of functions in a prior lesson, right? Composition of functions. We looked at decomposition of functions, and we're going to use that same skill for u-substitution. I am going to note that I am introducing this to you with the quadratic form. This is the first thing I'm having you all do with u-substitution is a quadratic form. However, this strategy is not isolated to the quadratic form. You're going to use this in a wide array of situations. A u-substitution is useful in your future math classes. So what do I mean? Let's do a decomposition here. Let's do a decomposition. You can see I have x of t. I was conceptualizing maybe a position. For me as a physicist, this may be a position with respect to time. All right, that's my function of position with respect to time as a function of time. And you can see I can have this weird stuff going on. I have this t minus 3, and then you may also see in here that there's a quadratic form. Do you all see the quadratic form in here? I have it to a squared power, and then a first power, and then to a 0th power. Okay, so here's what we're going to do. Is we're going to say that we're going to let a u equal a new variable I'm introducing. We're going to say u of t is a smaller portion of that larger function. We're decomposing it, right? So I can say u of t equals t minus 3. Okay, so then if I rewrite this in terms of u, if I say the position in terms of u is going to be u squared plus 3u plus 2. So x is a function of u, which is ultimately a function of t. Do you see how I could decompose that original function into two constituent functions? A larger one which contains that smaller one. So this is the u-substitution that I'm talking about, is you're going to pick out a smaller portion of that larger function and take it out and make it easier. You can see how this second function is a lot easier to deal with, and you may even see right away that I can factor it, right? U plus 2 times u minus, or u plus 1, right, would be how it factors. And if I even solve for it, I can solve for it, okay? But that's the larger ideas. I'm going to take a u, let it equal some smaller portion of my larger function. I'm going to decompose my larger function. And my tip here is whatever is to the power here in front or next to the b term in this quadratic form, that's what your u-substitution is going to be. That's my tip in there, okay? So let's do some examples. I like to do examples. Let's look at the general strategy overall as we're doing this. I have an example over here in the general strategy here. What we're going to do is recognize the quadratic form suitable for u-substitution. And so I put in a times something squared plus b times something squared plus c, right? Because our something is going to be our u-substitution. That's what we're going to substitute our u for. Okay, so with this example, I have x to the 4th minus 20 x squared plus 64. So what my suggestion is we're going to look at, right, overall I have something to the fourth, the squared, and then 0th power. This will be your u substitution. We're going to let u equal x squared. So if I rewrote this whole function overall, this whole equation, I'm going to get, well, u squared is x to the fourth. You're okay if I say that, right? If I square this thing, I'm going to get that stuff. So I get u squared minus 20u plus 64 equals 0. Okay, so I've covered the first three things here. Recognize the quadratic form suitable for the u substitution. So I have a times something squared times b times something plus c. So I saw that my something was x squared. I determined my appropriate substitution. That was this step here. I determined my appropriate substitution, and I transform the expression into a general form, right? So there I have a u squared plus bu plus c, and they're saying it's equal to 0. I can solve. You might be able to kind of recognize that now that I have it in the quadratic form this way, I can solve. 64 is a small enough number. I'm going to note that I can factor this guy. U minus 4 times u minus 16 equals 0, right? 4 times 16 is 64. Negative 4 plus negative 16 is negative 20, so that factored nicely. And so I get u equals 4, right? If I do this proper for you all and use a zero product property, u minus 4 equals 0, or u minus 16 equals 0. So I'm get u equals 4 or u equals 16. But what I'm going to tell you right now is that we're not done solving the problem. We did the substitution, and remember I said we have to undo the substitution. We need to transform back to the original variable. We don't care what u is. What we care about is what x is. We want to go back to the original substitution. So what I'm going to do is I'm going to take this expression and I'm going to bring it back down here. And I'm going to say, oh, u is 4. Well, u is also x squared. So I can say x squared equals 4 or x squared equals 16. And you may see why I picked this problem. The answers are really easy. So if I want to find x will equal plus or minus 2. I can take the square root of 4. Plus or minus 2. Remember, when you take a square root, you have to do the plus or minus. Or x equals plus or minus 4. And so we're going to get 4 solutions to this. When does this function cross the x-axis? That's what it's asking. When does this function cross the x-axis? Well, I use u substitution to find out it does it at positive and negative 2 and positive and negative 4. Of course, you know that I pulled up the graph for this. I'm going to bring it to the front and show you that where the answers are. And so there's my original equation, and I highlighted where it crosses the x-axis here. And you can see that I have plus and minus 2 and plus and minus 4. All right. So that's how to do a u substitution. Kind of clever, right? Kind of clever. There's this extra step in here, but as we get into more complicated functions, you're going to see how a u substitution is going to be useful for you. After I did that u substitution, I did factoring. I'm used to doing factoring. Factoring is an old friend right now. I could have factored this original function, could have, but let's move on to more complicated problems where we're going to do the quadratic form in a u substitution. So I have a second example here. We're going to notice that we are in a quadratic form. Do you see the quadratic form here? I have something squared. So I have a 1 times something squared minus b times that something to the first power plus c. Do you see that quadratic form in there? So my hint is to say whatever is to the first power here, make that your u substitution. So we're going to say u equals 5k minus 3. That's how I write my k's, because I don't want to confuse them with kappa. It's a physics thing, but that's how I write my k. It's not a weird r, it's a k, all right? K, okay. So u is 5k minus 3. So if I rewrite, I'm going to rewrite my original expression in terms of u now that I have that substitution ready. So I'll get u squared minus 9u plus 20 equals 0. On the previous problem we used factoring, we can use factoring on this problem. U minus 4, u minus 5 equals 0. 4 and 5 add up to 9 with a negative sign, and 4 and 5 multiply to 20. So we could just factor that. Very nice. So I can say that u minus 4 equals 0, or u minus 5 equals 0 with the zero product property. And then I can say u equals 4 or u equals 5. And I'm not done yet. What I need to do in order to find the k values that I'm looking for is to go back to my substitution, right? Go back to my substitution and undo my substitution. I know u equals 4, so that means 5k minus 3 equals 4, or 5k minus 3 equals 5. Okay, so I'm going to keep solving. Move the plus 3 over, plus 3, I get k equals 7/5. Real quick algebra there. I add 3 on both sides here. I get k equals 8/5. So those are going to be my two answers. And that's how you use u-substitution with the quadratic form. Okay? That's the algebra from it. I think if you were clever, you're getting clever here. You're like, I'm just going to graph this function. I'm just going to graph it and look at the equation. Well, let's see what the graph shows us. I think what I did was I graphed the original equation in terms of x. You all see in terms of x. Instead of k, I have x in there. And I asked myself, where does this cross the x-axis? Where is it equal to 0? Where does it cross the x-axis? And I can see it's 1.4 and 1.6, which is 7/5 and 8/5, right? It's over 1, right? So my graph verifies the two solutions that I solved there. All right, let's do another example. I like doing examples. Let's do a little bit weirder example maybe, that it might be harder for you to recognize the quadratic form in here. Again, we want an a times something, right? Something squared plus b times something to the first power plus c. Do you all see that something in here? What I'm saying is that it's going to be what is ever in front of that b term. So if I do a u substitution in this situation, I get u equals the square root of x. So that means u squared equals x. I think it's harder to see maybe with this example because it's not apparent right away, because this isn't a factor of 2 or a factor of 4. It's not an even factor. But it is if you're saying that x equals, or if u equals x to the 1/2 power, and then if I square x to the 1/2 power, I get x, right? X is the square of the square root of x. Okay, so no more ado about u substitution. Let's go ahead and write out our new transformed equation to solve with our u substitution. Wherever I see the square root of x, I'm going to put u. Wherever I see x, I'm going to put u squared. So again, this factors nicely. What is that? X plus 5 times x minus 3 equals 0. I'm going to use the zero product property again. X plus 5 equals 0, or x minus 3 equals 0. So x equals negative 5, or x equals 3. And you may do what I just did. Do you see what I just did? I'm going to leave this here as a mistake for you all to learn from, and don't do it. So we're not in terms of x, we're in terms of u. Sometimes I get sloppy and I get solving problems and I start writing x instead of the variable I'm using. Watch out for that. Because we have an x in the original equation, we're definitely using u down here for our u substitution. Okay, so now that we have u solved for, I'm going to go back to my original substitution and bring it back down here and say this, that u equals negative 5 and u equals the square root of x, so the square root of x has to equal negative 5, or the square root of x equals 3. We're going to toss out one of these answers. This may be why this is also a complicated problem for students, is that the square root of x, it seems like you could work with this. The square root of x is -5, so x would have to equal 25, but this does not logically parse. That's what we would say. It's not logical. It's not a true statement, and it has to do with the fact that taking a square root, and I'm not 100% sure on this, taking the square root doesn't result in a negative sign, but then there's other situations where we have to consider the negative sign. But what I am going to say is that this is an extraneous solution to this problem because it can't be true. And when we look at the graph, you'll see. All right. I can go over here and say x equals 9, right? I square both sides. In order to get x by itself, I get x equals 9. And this is going to be our only solution. Okay. So I think if you were just doing algebra, you might keep that 25 value. But again, we're going to look at the graph. We always verify our solutions with a graph. I'm going to bring this graph forward for you. And you can see here's the function. I graphed the original function in terms of x and the square root of x. Okay. And that's what it looks like. It looks like a weird square root and parabola together. Maybe, I'm not sure exactly what's going on there, but you can see it's asking where is it crossing the x-axis, and you can see it's crossing the x-axis only at 9. Only at 9. So I was definitely okay tossing out this extraneous answer, that not true answer that I wrote down there. We need to toss out. So when you're doing your algebra, always check with your graph so you're not including extraneous solutions. The last example I have here for you has to do with a kind of, more complicated. This is the second to last, actually. I have another one that I'm not going to solve, but this I'm going to go a little bit more and solve for you. With you, we'll get to a certain point where I've solved enough for you to take it off on your own. Okay, so this is kind of like the original example that we looked at. You can see that there's a 4 here and a 2 here. So I can say that this is a something squared and this is a something to the first power. What I suggest is you're going to take this whole thing and let it equal u. U equals -3x plus 2 quantity squared. So you can see that I'm really taking advantage of this u-substitution where I'm choosing u to be an ultimately complicated function in itself overall. And so when I go to plug in my u into my equation to do my u-substitution, I get 10u squared. This term is the original one squared. So that'll be 10u squared minus 23u plus 12 equals 0. All right, so you can use the quadratic formula on this. We can't divide by 2 because that doesn't easily divide by 2. You could use a quadratic formula on this. I saw 10 and 12, and there's not a ton of factors of 10 and 12 that go into 10 and 12, and I'm going to magically wave my hand and say that this factors into 5u minus 4 and 2u minus 3. All right, so that's the magic of movie making, is I know the answer immediately, right? It's written down here in my notes. So that's what this factors into. I'm going to use the zero product property again and say that either of these terms has to be equal to 0. All right, and then I can solve 5u equals 4, u equals 4/5, or 2u equals 3, so u equals 2/3. Those are true. Okay, but I am not done yet. I still need to take into account this final step, right? I still need to solve for x. I don't care what u is, I care what x is, okay? So if u is equal to this stuff and u is equal to these numbers down here, I still have some algebra to do. I'm going to say that -3x plus 2 quantity squared equals 4/5, or -3x plus 2 quantity squared equals 2/3. Now I'm going to solve for x for both one of these. I'm going to solve down. In order to isolate, I need to take the square root and then remember to take a plus or minus. So 3x plus 2 equals plus or minus, what is that, 2 over the square root of 5? Is that what that is? Kind of weird, but that's true. Let's keep solving. Negative 3x equals negative 2 plus or minus 2 over the square root of 5. I'm going to divide by negative 3 on both sides, so I get negative 2 plus or minus the square root, 2 over the square root of 5 over negative 3. So I get x equals 2/3 plus or minus. I can move that root 5 up top, I guess. Let's move that root 5 up top. So I get plus or minus 2 root 5 over 15. And it's still a plus or minus. Even if you divide by a negative, you're still going to have a plus or minus. So that may seem like kind of a weird solution, but it is what it is. It is what it is. So that gives me two solutions. Another thing that I will do is solve over on this side. Of course, I'm going to solve over on this side. So I'm going to take the square root on this again. Take the square root, plus minus. Negative 3x plus 2 equals plus or minus the square root of 2/3. I'm going to subtract 2 over to this side like I did over on the other solution. So I get negative 2 plus or minus the square root of 2/3. I'm going to divide both sides by negative 3, so I'm going to get 2/3 plus or minus. I mean, I get lazy sometimes without having to do algebra here, simplification. You can just leave it like that. There'd be a root 3 at some place, right? So these are the four answers. There's 4 answers here. And what I'm going to tell you is the number of answers, and you might be catching on to this, the number of answers you expect is the largest number of x in that function. We'll study that a little bit more as we move towards polynomials. But do you see 4 answers here? I have a plus or minus there and a plus or minus here. So that results in 4 answers. And pals, wouldn't you know, I have the graph here. Took up all of that. The graph here, you can see that there's 4 solutions. This is a polynomial of order 4, and you're seeing that it crosses the x-axis here in 4 places. Where does it equal 0? Those 4 places, right? So that corresponds to our algebraic solution. I think if you multiply those through and add them through in a calculator, you're going to get those decimal values, but that there's 4 of them is what I wanted to look at. The last problem here I wanted to help you set up. I'm not going to solve this for you, but I'm going to help you set it up. It's a little quirky, right? Do you see the quadratic form? Do you see that this exponent is twice times this exponent? Negative 6 equals 2 times negative 3. That's how I know I can do a quadratic form. And then I have an x to the 0th down here, right? There's no x. X to the 0th is 1 power, right? So in this situation, I would let u equal negative 2x minus 1 to the negative 3rd power. That's what I would let u equal. So then when you plug in your u-substitution, you can see that this becomes factorable. A factorable quadratic equation. What is that? 6u plus 1 and 4u minus 1. That'll give me a negative 6 and a positive 4, which add up to a negative 2 equals 0, and so forth. I guess you get u equals negative 1/6 and positive 1/4, and then you can take those values and set them equal to this, right? So you'd say negative 2x minus 1 to the negative 3rd power equals negative 1/6, and negative 2x minus 1 to the negative 3rd power equals 1/4. I actually would flip those. Pretty clever here. So negative 2x minus 1 to the 3rd power. If I take this and invert it and take this and invert it, that doesn't mean take the negative sign of it. It means invert it, right? I'm going to flip it. So that this turns into a positive 3, and then this turns into a negative 6. And you can play the same game over here, right? Negative 2x minus 1 to the 3rd power has to equal 4. Okay, and then you can solve from there. I'm going to trust you to be able to use your algebra with exponents, taking a cube root and simplifying down in order to find those answers. But that's how I would set up that u-substitution. And I hope this lays a really strong foundation for you to recognize and use u-substitutions in the future. Quadratic forms is not the only place where you're going to use u-substitutions, but getting used to the utility of a u-substitution and what you have to do in order to do a u-substitution and undo it is what I'm setting the foundation for.